Okay, so thanks for joining me for lecture number 16. In lecture number 15, we were looking at failure of brittle materials. But most of the materials that we've been dealing with in the problems in this course have been ductile metals. So we're going to spend the next couple of lectures looking at failure theories that are applicable to those materials. So for our ductile metals, we have two failure theories that we can apply that we're going to cover. In this lecture, we're going to look at the absolute maximum shear stress theory. So we've got two failure theories. We've got the absolute maximum shear stress theory, which we'll do this class, and we've also got what's called the maximum distortion energy theory. And we'll do that one next class. So for the absolute maximum shear stress theory, the idea behind this theory is really simple. What the idea is that normal stress does not cause failure of ductile metals. It's the shear stress that causes failure. Okay, so not normal stress that causes failure, but rather shear stress. Right, so you might wonder why a theory like this would be developed. So if you do something like we did in lab number 1, where we just had a rectangular piece of metal and we applied an increasing tensile force F and took the material past its yield point up into plastic deformation, then what you see developing are these bands along the material or lines that are oriented at 45 degrees to the horizontal. And these are what are called slip planes. And what's going on here is after the material reaches its yield point and starts plastically deforming, within the atomic lattice work of the metal, dislocations are forming, what are called dislocations, where you've got rows of atoms that are being split and joined up with other atoms. And as those dislocations pile up, they create these slip planes that are visible on the surface of the metal. So the observation that these visible sort of lines oriented at 45 degrees are associated with taking a ductile metal above its elastic limit or above its yield point, you can start to understand why one would think that this was associated with shear stress. If we look at any point within an object under a tensile load, so here's our little element, right? We know that it's just under a tensile stress sigma, and we can plot that stress on Mohr's circle. Let me get my straight lines going here. Okay, there we go. So the center of the circle is going to be located at the average normal stress, which is whatever the value of sigma is, divided by 2. It's the center of the circle. And then the reference point, point A, is the stress on the right-hand side. So that's right here at the origin. And then the radius of the circle extends from C to A, and the circle ends up looking like that there. So here we can see that the maximum shear stress for an object under only uniaxial tension is located at a distance around the circle of 90 degrees, which is a 45-degree inclination in reality, right? So that's matching up with the plane that these, or the direction that these slip planes are forming. So that was the thought behind the fact that it's not the normal stress present that's causing these materials to undergo failure and failure being yielding, but it's actually the maximum shear stress present when the material reaches its yield point. Okay, so what we can do is we can figure out what tau max was at the point when we reached the yield stress on the stress strain diagram. Okay, so if tau is causing failure, meaning yielding, what we describe failure as for a ductile material, then what was the value of tau max when our stress that the element experienced was equal to the yield stress? And I'll write that as sigma yield instead of sigma y, just to not confuse it with the stress in the vertical direction. It is in the vertical direction, but just to specify that I'm talking about the yield stress there. So we can ask, what was the maximum shear stress when the stress that the element was experiencing hit the yield stress? And that's easy to do from Mohr's circle here. So we know that tau max is equal to the value of the radius, and the value of the radius is equal to the value of sigma divided by 2. So when our stress equals the yield stress, then we've got tau max is equal to yield strength divided by 2. Okay. So what we can do is use this to say that failure of the ductile material, this ductile metal, if it's occurring due to shear stress, then that failure will occur when the maximum shear stress present reaches the normal yield strength of the material divided by 2. And what the maximum absolute shear stress theory says is that we can take the right-hand side of this equation, the yield strength divided by 2, and say that failure in a ductile material will occur when that material is under a more complex loading situation, when the maximum shear stress reaches that value. So, in other words, theory says failure will occur when absolute maximum shear stress in a material reaches the maximum shear stress that was present at the yield point during a tensile test. Of that material. Okay, so putting that into shorter form, we say that failure will occur when the absolute maximum shear stress reaches the shear stress at the point when the yield stress occurred, which we just determined was equal to the yield stress divided by 2. Now, if we have a safety factor, we can put this theory into a more useful form. So including our safety factor, SF, then we have tau abs max equals sigma yield divided by 2 times the safety factor. So that is our statement for what the absolute maximum shear stress theory is. Now, we've talked a lot about what maximum shear stress is, but I've just thrown in this extra term here, absolute maximum shear stress. So we should talk about what that is. So what's absolute maximum shear stress? Okay, to explain that, I want to show you something here using an in-plane element here. Now, we'll use a volumetric element, actually. So let's say we have a volumetric element that's like this, and let's define some directions here. So we've got X, Y, and Z. And let's say this particular element is experiencing only principal stress is one stress in the X direction, like this, and a stress in the Y direction. Let's say the stress in the Y direction is larger than the stress in the X direction. So I'll show this with a slightly larger vector here. Okay, don't really need that label down there. Okay, there we go. If I asked you to plot Mohr's circle for this element and tell me what the maximum shear stress was, you'd do the following. So you'd draw the in-plane version of this element that would be in the XY plane here. So here's XY, and you'd have your stress sigma Y here, and your stress sigma X there. And let's set up our axes for Mohr's circle here. Positive shear stress, positive normal stress. And you'd calculate what the average normal stress was, and that's something in between sigma Y and sigma X. So if sigma Y, I'm just going to pop the value of sigma Y on here, and let's say sigma X is maybe this value here, then the average normal stress is the average of those. So it's located right in the middle. So there's our location for the center of the circle C, and this is sigma average. Okay. And then you'd plot the stress on the right-hand side of the element, which is sigma x, and that would be our reference point A. And then the circle extends from C to A, and we've got more circle that looks like that, going between sigma x and sigma y. And the maximum shear stress here is, I'm going to do everything for this circle in blue, and you'll see why in a second. The maximum shear stress here is up here, tau max. Okay, let's make that, oops, don't need that big eraser, there we go. Color that blue, there we go. Okay, now what I want to show you is that for a material, or for a point in a material that's under a loading situation or a stress situation like I've just drawn there, this value of tau max is not actually the largest shear stress that occurs, even though it's the largest value of shear stress on Mohr's circle. There's a larger shear stress that you're not seeing by drawing this particular in-plane element, or the Mohr's circle for this particular in-plane element. So what I want to do is draw the Mohr's circles for the other in-plane elements that we could have chosen. So we drew this circle here for the XY plane. But what if we drew Mohr's circle for this element in, let's say, the XZ plane instead of the XY plane? Well, if we chose the XZ plane instead, so that's a plane that looks like this. I'm going to draw it, imagining I flip the element like this. And if I draw that in-plane element here, then sigma y just appears as a dot on the surface of that element, so it doesn't show up. And the only stress that we get is sigma x, like this. So if I take the average normal stress for this, it's right between sigma x and the origin. So here's my circle for this second option. So I'm going to draw the Mohr circle for the XZ plane in red here. And then the right-hand side gives me my point A, so that again is over here. And then my circle extends. So let's just specify that this is sigma x divided by 2, which is sigma average. Oh, I could do a better job of doing that and not have it be so cramped. Okay, there's sigma average equals sigma x divided by 2. And our circle extends from point A through the origin and back around. Okay. There we go. Let's try one more time for that. There we go. Okay. Here's our radius r. But what if, we've got another option, what if instead we chose to draw the element in the YZ plane? So we've got Z here and Y here. Then we'd see our element, and sigma x would just appear as a dot, and we'd only see sigma y. Okay, so I'll draw that one in black. So sigma y is out here, and the average stress is, or the center of the circle is going to be located at sigma y divided by 2. Let's say that that's there, sigma y divided by 2, okay? Then we plot the stress on the right-hand side as point A, so point A's back at the origin here, and our circle extends all the way from here around like that. Now let's try that again. Almost. One more time. That's better. Okay, there's the third and final circle based on the YZ plane. Okay, so again, this was normal. What we do is the normal in plane element. And this, in this case, this was in the XY plane. This one here was the ZX plane. And then here we have the ZY plane. And what you can see is that for the ZY plane, if we draw more circle there, we have a much higher, much greater shear stress than we had for our normal in-plane element. So going through the process of drawing 3 more circles for our element, considering all the different possible planes, the largest of those shear stresses is what's referred to as the absolute maximum shear stress. So this is the absolute maximum shear stress. Now, does this mean that every time you do a problem now, you need to draw 3 more circles instead of just 1? And the answer is no. The absolute maximum shear stress is only larger than the maximum shear stress that you draw for your normal in-plane element when you've got a state of biaxial normal stress like you do in this element, where you have normal stresses in 2 different directions that are either both tensile or both compressive. And we'll talk about a situation where you find that in a moment. But for situations when this occurs, where you've got a state of biaxial stress, then the absolute maximum shear stress always ends up being the first principal stress that you would have calculated from your normal in-plane version of Mohr's circle divided by 2. See, tau max here is equal to the radius of the larger circle, which is sigma y divided by 2. And the first principal stress for a normal in-plane element here is sigma y. So the absolute maximum shear stress here can simply be found by drawing this normal version of Mohr's circle and taking the value of sigma y and dividing it by 2. Okay, so rule for tau abs max. So we draw Mohr's circle for our normal in-plane element. And then we calculate our 2 principal stresses, sigma 1 and sigma 2. Okay. if sigma 1 and sigma 2 both have the same sign, so if they're both positive or both negative, then tau abs max is equal to the first principal stress, or the larger of the two absolute values, divided by 2. If, on the other hand, the two principal stresses have opposite signs, then the absolute maximum shear stress is equal to what you'd calculate as the maximum shear stress for your normal in-plane element, which is equal to the radius of the circle. So there's two very easy rules here that you can apply to find the maximum absolute shear stress. Simply draw a Mohr circle for your normal in-plane element, calculate your principal stresses, then if they both have the same sign, so either they're both positive or they're both negative, the absolute maximum shear stress is the first principal stress divided by 2. If they have opposite signs, meaning that your Mohr circle for your in-plane element straddles the vertical axis, then your absolute maximum shear stress is simply equal to the maximum shear stress on that circle, which is equal to the radius. Okay, so let's do an example to show you how this theory is put into practice. Example. Okay, in this example, we're going to have the following. We're going to have a rod here that is fixed to a wall, and it's going to have a diameter of 1/2 inch, and it will be subjected to an axial compressive load of 3 kip and some torque T. Now this is going to be a 304 stainless rod to be loaded as shown. And what we want to do is, using the absolute maximum shear stress theory, we want to find out what the maximum allowable value of the applied torque T can be for a safety factor of 1.4. So using the absolute maximum shear stress theory, we want to determine maximum allowable value of T for a safety factor of 1.4. Okay, so we know what the absolute maximum shear stress theory states. Failure will occur when the absolute maximum shear stress in this object equals its normal yield strength divided by 2 times the safety factor. So the question that we have to answer first is, which point in this rod is going to experience the greatest absolute maximum shear stress? So you think about these two applied loads separately. So first of all, the 3 kip axial compressive load, we know that's going to create an internal normal force that's equal to 3 kip, and all points in the cross section are going to experience the same normal stress resulting from that internal normal force, and the value of that normal stress and the value of the normal force isn't changing with position along the length of this rod. So we could pick any point that we wanted and it would be the same, just considering the applied axial load. For the torque T, we know that torques produce shear stress that's greatest around the circumference. So we could pick any of these points around the circumference or any of those points actually over the entire length. So all points on the surface of this rod over its length experience the maximum shear stress. So we just want to pick one of those to analyze. Okay. So let's just make a note of that. So all points over surface along length experience maximum value of the absolute maximum shear stress. So we just pick one. So we'll pick one and we'll call that point A. So let's just pick this one right here. So there we go, point A. So there's our point. Let's do a little bit of erase and replace now to change this into a free body diagram. So what we want to do is we want to take a section cut through point A there to look at what the internal forces are, and then we'll draw our volumetric element and put the stresses in on that. So let's just get rid of this stuff here, and we know we're going to have at point A, and we'll just move that label out of the way a little bit and put it there. So at point A, we're going to have an internal normal force that's 3 kip, and then we're going to have an internal torque that's in that opposite direction. So let's draw our volumetric element now for point A. So what our volumetric element will look like is something like this. There we go. And just to get you oriented here, the face of the element that's in the section plane is the face that I'm outlining in red right now, the right-hand face of that element. So thinking about the stresses that this element is under, from the internal normal force, we're going to have a normal compressive stress. So this is the stress from the internal normal force, sigma subscript n. And then from the torque, we're going to have a shear stress that's oriented upwards on that face, tangent to the circumference in the direction of the torque, and then all of the 3 other shear stresses that need to be present to hold that element in static equilibrium. So there we go. We've got our volumetric element done. Now we always want to define some axes here that we're working with. So let's take 2 like that and then another like that. So this is X, let's say Y, and Z. All right, next step would be to figure out what the values of the 2 stresses are. So we've got sigma is going to be equal to n divided by A, 3000 divided by pi over 4 d squared. 1, not 1/4, 1/2 inch squared. Okay, so let's see what that gives us. That gave me, when I did it, 15.3 kSi. And the shear stress, tau, due to torque T, is going to be given by TR over J, because we're at the circumference there, so variable rho becomes R, and we've got t, which is our unknown. R is 1/4 j pi over 2 radius to the 4th power. So radius to the 4th power. So we can get rid of that and make that one a 3 there. And that gives us 128 over pi multiplied by t. And let's think about what unit that's in. That's going to be in PSI if t is in units of pound inches. So let's make a note of that. So that's if t is in units of pound inches. So we'll remember that those are the units of t when we end up solving for it. Now, before we move to the next page, let's just pop our values of stress over here. So we've got 15.3 KSI, and our shear stress is, what, 128 over pi t, and that's in PSI. So let's go ahead and clip that out, and we'll take it with us onto the next page. Go, copy, and pop it on this page. So to draw Mohr's circle, we need to take that in-plane or volumetric element and make it an in-plane element. Now, remember, we're going to be interested in the maximum absolute shear stress, or the absolute maximum shear stress here. I always get that mixed up. We're going to be looking for the absolute maximum shear stress here. So what you want is just the normal in-plane element that you draw Mohr's circle based on, the one that captures all of the stresses in this diagram. So that's the one in the XY plane, and that's easy to draw. We've got just one normal stress, sigma subscript n, and then our shear stress on this side goes upwards, downwards, to the right, to the left. So this is tau due to t. Okay, values of those are as shown on the left. All right, so now let's set up our axes for Mohr's circle here. So here we go. This is positive normal stress. This is positive shear stress there. So the first thing that we need to plot Mohr's circle is where the center of the circle exists, and that's given by the average normal stress, right, which in this case is half of, we're in the XY plane, so it's half of sigma x plus sigma y, the average of those. And that is the value of sigma n, 1/2. Now it's compressive, so don't forget to put it in as a negative, 15.3 plus 0. Okay, so what does that give us? That gives us 7.6 KSI there, minus 7.6 KSI. So we can plot that. Let's say right about there, minus 7.6. And there's the center of our circle. Next thing we plot is the stresses on the right-hand side, which give us point A, our reference point. So A given by sigma comma tau for the element's right-hand side, which in this case is the normal stress. Again, remember it's negative because it's compressive. And then our shear stress is upwards on the right-hand side, so that's a positive shear stress. So we've got plus 128 divided by pi times t. And again, don't let the fact that this has a variable in it bother you. You know it's some positive value, so just put it somewhere on that y-axis or the shear stress axis. So let's plot that point. So minus 7.6, we're going to double the distance for point A. So here's minus 15.3. And then we're going down here to, let's say it's about there, 128 divided by pi now if we want to put these in equivalent units, we've already plotted this in KSI. We want to plot tau in KSI as well, then we better put a 1000 there in the denominator to put into units of KSI as well. So we can figure out where that point A is. So it's going to be about there. Now let's try and draw that Mohr circle. Okay, so going through A, around C, like that. Perfect. All right, so now what you can see, the radius extends from C to A. Okay, there's our radius R. Now the distance here between the origin and the center of the circle is 7.6, obviously. And the radius is, the radius here, this distance, is longer than 7.6. So we know that one principal stress, in this case the smaller one, is going to be positive, and the other principal stress, the negative one, is going to be a larger absolute value. So that's the first principal stress. So the principal stresses in this case have opposite signs. So tau abs max is going to be equal to the maximum shear stress that occurs. And where is the maximum shear stress? It's just this one here, or this one down here, doesn't matter which. And that is equal to the radius of our circle, which is easy to find. Okay, so let's apply our failure theory now. So we had tau abs max is equal to sigma y divided by 2 times the safety factor. Okay, so the absolute maximum shear stress is equal to the maximum shear stress is equal to the radius of the circle. The radius of the circle is easy to find. We're looking at the square root of, what do we have here, 7.6 squared plus 128 pi over 1000 squared. Okay, so we've got the square root of 7.6 squared plus 128 over pi times 1000 t squared 1/2. Now we're working in units of KSI now, so we want the yield strength on the other side to be in units of KSI. So 304 stainless steel, let's get that from our material property table. There's 304 stainless, yield strength 30 KSI. We've got 30 divided by 2 times the safety factor of 1.4. So solving that for T gives us 184.4, and that would be pound inches like we said before, which is, let's see here, 15.4 pound feet. Okay, so there we go. That's the torque that we can apply to have maximum torque that we can apply for a safety factor of 1.4. So just looking back here, this was a case where our principal stresses had opposite signs. We had sigma 2 being positive and sigma 1 being negative. Now, and in this case, our absolute maximum shear stress was our maximum stress, so at the top of Mohr's circle. So the other the other rule for absolute maximum shear stress was if that didn't happen, and the two principal stresses were the same sign, then we'd simply take the absolute maximum shear stress to be equal to the first principal stress divided by 2. So let's look at a situation when this would happen. Okay, so situation when the two principal stresses are actually the same sign. Okay, so that takes us into a quick look at thin-walled pressure vessels. Okay, thin-walled pressure vessels are things that hold fluid under pressure, like your propane tank, and they have, let's draw this horizontally actually, save some space, and they have a relatively thin wall thickness of the material in relation to their radius. So here's our tank, and it's got fluid in it that's under pressure P, and this is the radius of the tank R, and here is the wall thickness T. Okay, so we'll say that this is the gauge pressure here within the tank. And the gauge pressure within the tank is simply the difference between the absolute pressure in the tank and the atmospheric pressure. So we always, or we most often reference pressures relative to normal atmospheric pressure. So that gives us the gauge pressure. Okay, so let's look at what the stresses are like in the wall of a tank that's containing fluid under pressure. Okay, so thinking about this, we have, I'm just going to draw that tank again. If we look at, and I would draw it without drawing the actual wall here. If we look at any point in the wall, let's say it's a point here, up at the top. And let's draw the volumetric element for that point. So maybe it looks something like this here, where the top of the element there is on the outside of the tank, and the element's going through the full thickness of the wall. So this would be the outside surface, and then the bottom here is the inside surface. Okay, we've got pressure within the tank, so we've got pressure pushing on both of the ends of the tank here, and that's acting to elongate the tank. So we're going to have a stress that's tensile and is in this direction here at point A. And that would be the same regardless of which point in the tank we chose. This stress we'll call the longitudinal stress, sigma subscript L. Now, we've also got another stress in the wall. If we take the tank and sort of chop it in half through point A here, okay, our pressure is also acting out radially like this, and that pressure is, or the pressure in that direction is acting to expand the circumference of the tank. So we've got a stretch happening in the other way. So there's also a tensile stress in this direction, and that is called the hoop stress, sigma subscript H. And then you might think that there'd also, if we think about point A as being this little bit of material here, right, point A, then we've got pressure directly acting on that inside surface. So maybe we should have a stress here, sigma R, for the stress in the radial direction. Now, the problem with that is that if this tank has a sufficiently thin wall, then our element here can be taken to go through the full thickness of the wall, as I've shown. And if there's a stress in the radial direction on the inside of the surface, there's no stress that can be present on the outside surface to balance that. For example, we can't have a stress sigma R on the outside surface balancing that, because the outside surface is just touching air and there's nothing to apply that. So if we can't have that stress on the outside there, then we can't have a radial stress on the inside as well. So the removal of that stress, that radial stress on the inside of the tank, that's where this thin wall assumption comes in. So if I just draw that back in here, sigma R, okay, this goes to approximately equal to 0 if the radius over the thickness of the tank is greater than or equal to 10. So that's the thin wall assumption. So IE is or has a thin wall. Okay, so for these pressure vessels that are classified as thin wall pressure vessels, it's very easy to build an equation up that relates gauge pressure within the tank to stress in the wall. So let's just do that. Okay, so let's get equation for the longitudinal stress first. The longitudinal stress was sigma L. Okay, again, really easy to do, so this won't take long. So here we go. We've got the, actually I'm going to draw that a little bit bigger. Okay, here's the rest of the tank going over like that. So I'm cutting the tank in half. So over this internal surface that I've drawn, over this surface that's here, we've got pressure acting on that surface. So this is pressure P acting on that surface. And we know that the state of the wall here is going to be under a state of longitudinal stress pulling back the other way. So if we want to do a sum of the forces equation in the x direction, balancing those. So let's just do sum of the forces in the x equals 0 here with, we'll say that this is the x direction, that's the y direction. Then what do we have? We've got the force acting to the right comes from the pressure. And to take that pressure and turn it into force, we need to take pressure and multiply it by the area that it's acting over. So it acts over this whole internal surface there, which is pi r squared. And that's balanced out by the stress, the longitudinal stress, multiplied by the area that that's acting over. Now, the area that that's acting over, this red hatched area, the way you'd get that area would be to calculate the circumferential length here, and then multiply that by the thickness. So what you're really thinking of doing is sort of if we clip this section down that way and unroll it, then you get a rectangle of material that is the circumference long by the thickness thick. So we've got 2 pi r here t. So 2 pi r t. Okay, pi's go, r squareds go, so sigma L is what? P r over 2t. So there you go. I told you it was easy. So there's our equation for longitudinal stress. Situation's not much harder for hoop stress, right? We can pretend now that we're going to make an additional section cut here and just cut out a sliver of that tank or a longitudinal section. Okay, here we go. So something that looks like this. And then what I'm going to do is I'm going to section cut this again like, nope, not going to do it like that. It's going to make the drawing harder than it needs to be. So I'm going to section it like this. There we go. So we're going to have a picture that looks like, maybe move that back a little bit. Okay, there we go. There's one cut through the tank. Here's the other cut through the tank there, and then we've got, right, something like that. Okay, so now we've got pressure that's acting over this face here, right, acting on that face there. There's our pressure P, and we've got stress, hoop stress, in the tank wall that's acting in the opposite direction, and it's over that area there. Okay, so pressure is acting over this area here. So again, let's do sum of the forces is equal to 0 here. So we've got P, and the area that it's acting over is 2 times the radius, 2r, so that's this distance here, right, the diameter, 2 times the radius, and then some length, L. Let's just make this length L. There we go. So P 2r L. And then balancing that, we've got our hoop stress multiplied by the area that that's acting over to change that into a force. So that's going to be, what this is, thickness T. So we've got thickness T multiplied by length L multiplied by 2, because there's 2 of them. Okay, 2's go, L's go, and sigma H is equal to PR over T. There we go. So you've got the equations now for how to deal with a thin-walled pressure vessel and find stress at any point in the wall if it's a cylindrical tank. If it's a spherical tank, and there are some of those, then any cut through a spherical tank that you make ends up looking like the cut that we made to find the longitudinal stress, and you end up with stresses of PR over 2T. But for any cylindrical tank that's a pressure vessel, thin-walled pressure vessel, then the equations governing the longitudinal stress and the hoop stress are these two here. And note that compared to the hoop stress, which is PR over T, the longitudinal stress is 1/2 of that, PR over 2T. Okay. This is when you barbecue a hot dog, and here's your hot dog that you're barbecuing, and you will find that if you leave it on the grill long enough, you will get a split that develops longitudinally like that. That's because as steam is produced within the hot dog, and you've got the thin casing around it, it becomes a thin-wall pressure vessel, and the stress in the hoop direction is twice the stress in the longitudinal direction. So you will always get that split occurring like that and never like that. There you go. It's good weather for barbecuing now too. So very, very timely lecture for us. Okay, so let's do an example to show a situation where you have two principal stresses that are the same sign. In this case, spoiler alert, they'll both be positive because it's a pressure vessel question. Example. Okay, so here we are going to have a tank, cylindrical tank. Wow, that's bad. Let's try this approach. That's a better way to draw them. A cylindrical tank made out of A36 steel, and is going to be holding a pressure, a gauge pressure of 5 megapascals. Wall thickness, T is going to be 25 millimeters, and the radius, R, is going to equal 3/4 of a meter. Okay, so what we want to know in this question is simply what is the safety factor for this tank? And we'll say use the absolute maximum shear stress theory. Okay. Right, so again, the absolute maximum shear stress theory is tau abs max is equal to normal yield strength divided by 2 times the safety factor. So all that we need to do is figure out what the absolute maximum shear stress is, or the point that experiences the greatest absolute maximum shear stresses in this tank, and then apply our equation, having retrieved the value of the yield strength from the material properties table. Okay, in the tank wall, all points are under the same stress, so this is the nice thing about pressure vessels, they're dead simple. So we'll take this point as an example, and we know that we've got stresses sigma H and sigma L, like that. Now, that is only true if the pressure vessel meets the thin wall assumption, where radial stress is 0 in that case. So let's check the thin wall assumption before we calculate those two stresses. So check thin wall assumption, right? So the assumption is that the radius over the thickness has to be greater than 10 for this to be considered a thin wall. So let's pop in the numbers here. So we've got 750 divided by 25, and that's that given us 50 divided by 25. So that's 30, which is greater than 10, so no problem. So this is indeed thin-walled. All right, so we can proceed with calculating what our hoop stress and longitudinal stress are. So for the hoop stress, sigma h equals PR over T. We've got 5 megapascals times 10 to the 6. Our radius, 3/4 of a meter, divided by our thickness, 0.025. That's giving us, what, 150 megapascals. And now it's easy because you don't even have to put in any work to calculate the longitudinal stress. You know that it's PR over QT, which is 1/2 of our stress in the hoop direction, or hoop stress, which is 75 megapascals, half of 150. Okay, and now things continue to be super easy because let's just draw our in-plane element again. So we've got our longitudinal stress. Sigma L is 75 megapascals, and our hoop stress, sigma H, is 150 megapascals. And there's no shear stress acting on the element. So when you go to draw Mohr's circle here, let's do that in black. Plus sigma plus tau. There's no shear stress acting here, so you know that these two stresses are the principal stresses, right? This equals your first principal stress, sigma 1, and this equals your second principal stress, sigma 2, because there's no shear stress. So this element, because it doesn't experience shear stress, it is showing you the principal stresses. So we can just put those on. So we've got, let's just put the values on actually. We've got 150 here, and half of that, 75 there, and our circle just goes between those 2 points. We could do a better job than that. Like that. Okay, there's the circle there. If you calculate the center of it's right in the middle. C, and if you were actually going to put point A on, reference points the right-hand side, that's sigma L, so there's point A. Radius goes from C to A. But we don't really care about Mohr's circle much for this problem, other than the fact that the two principal stresses are both positive. Okay, so both positive, and therefore our absolute maximum shear stress in this question is equal to the value of the first principal stress divided by 2, which is 150 divided by 2, which is 75 megapascals. So now we can go ahead and apply the theory. We've got tau abs max equals sigma y divided by 2 times our safety factor. The absolute maximum shear stress, 75. Let's clean that up a little bit. 75 times 10 to the 6 is equal to yield strength. Let's pop over and look at A36 steel in metric. Okay, A36 steel, 250 megapascals. 250 times 10 to the 6 divided by 2 times our safety factor. Okay, so solve that, and we've got 1.9 6.7. It's a safety factor. Okay. That shows you one scenario in which you have to use the other method of finding, or the other approach for finding the absolute maximum shear stress, which is simply to divide your first principal stress by 2. Because in this situation, if you were to draw that in-plane element from the other 2 perspectives, you get the 2 other circles, one that's a smaller one, but then the other one that's a bigger one. So this is that tau abs max that's really hidden from view when you're drawing the normal in-plane element. And again, this only happens where you have a maximum shear stress that's higher than the one you've drawn for your normal in-plane element if both the principal stresses are either positive or negative. Okay, so that's all for this lecture. In next lecture, we will look at the maximum distortion energy, also another failure theory for ductile metals. And we'll talk about a bit about the differences between that failure theory and this one that we've just done. All right, I'll see you then.